As I was saying a minute ago before starting, this week we've got a few things going on, right? Right now we're doing this lecture on algorithms. There's another video that I'm encouraging you to watch. I'm not going to show the video in class, right? But that doesn't mean it's not important. The only reason why I'm not showing the video in class is because you can watch this anytime, right? I've given you the video. All the other classes have the video. I'm not going to show it in class, but I'm strongly encouraging you to watch it. It's 4 minutes long. So, you can watch it while you're waiting for your coffee to get prepared. It's not. And then there's this other link that I'll refer to in a minute. Now, this link will take you to studio.code.org, and you'll see this number here, DNC FDT. That's our section, right? So other people are on code.org, but our section has this unique number. And so that's why I want you to just follow that link. And when you follow that link, it'll ask you, well, I'll just show you. It'll ask you to give a name and a password and your age and gender. And then you're just going to register, and it will put you automatically in this course. Now, at the end of this lecture, I'll talk about that a little bit more. So let's get started on the lecture then. So did I turn on the recording? Yes. So we're going to talk about algorithms, and algorithms being one of 4 components in our model. And I'm stressing in our model because it's a model. We talked about abstractions, right? I mean, there's the real world of computing, and there's the real world of computational thinking. And somehow we have abstracted that down to a model which has 4 components. Somebody else might abstract it down to something else, right? So this is not, it's not something that would never change. I mean, so after some review, people might look at that and say, well, it'd actually be better if we had a 5-component model or a 3-component, okay. So I'm saying this works for us now. We like it, but it's like that. It's a model that represents computational thinking. And so as it says there's the 4th pillar of computational thinking. These 3 here, we have discussed in the last 2 weeks, right? So decomposition, that is taking a complex problem, breaking it down into smaller components, solving those components, and then we put them back together and we've got our solved complex solution. Abstraction, that's, we said it was by applying layers, but every time we apply a layer, we actually remove some of the detail. And so we're removing detail till we get to the level of detail that is relevant to what we're trying to do. And so in last lesson, I mean, the really, really good example, I think, in the last lesson was the one of the fellow Leonard Euler, when he had to come up with the best way of visiting all 4 parts of Königsberg without going over the same bridge 3 times or more than once. And yeah, I mean, he had the big map of Königsberg and with all the town, all the little streets and all the buildings on it. And he just abstracted that down to 4 little blocks and some lines between them. And so that was all he needed for the job that he was doing. All right, so I guess when we say recall, apparently in lecture 4, we have actually made reference to an algorithm before. And so this should not be totally new to you. You've sort of heard of this before, I hope. With plain English, it could be an algorithm. So step-by-step instructions for how to do something, like a recipe. That could be an algorithm. Actually, yeah, recipes, chemical procedures. You'd have algorithms for that. Mechanical procedures, for, fixing, if you're servicing a motor vehicle, you do it in certain things have to be in the right order. And there's a lot of sort of instructions there that would work. Pseudocode is kind of like English. And actually, we used to call it structured English. Structured English sort of equaled pseudocode. And I hope that you get the idea out of that. What we meant by structured English is it's like writing English, but we've got a bunch of rules, and we do things in a certain way. So it's not just English, it's structured. And so we indent things. We start and end with a start and end. If something is part of, if there's a module that's part of something that's called more than once, for example, we're going to indent that in there. So that's pseudocode. And then flowcharts, which I think you saw as well. Flowcharts is really nice. And that's taking the rule thing even a bit further, because the shapes that you see in your flowchart have a meaning. And so a certain shape will mean a connector, a certain shape will mean inputs and outputs, a certain shape will mean a process. And so, yeah, so I guess, yeah, it says here, I'm just showing you these notes. I think I told you I'm not supposed to give you these notes, but I think I can show them to you, right? So there you are. Pseudocode is easy to read with some abbreviations. Flowcharts, yeah. I mean, I don't see what the big secret is, but there you are. Algorithm in plain English. This is looks like a recipe, right? Except it doesn't include the ingredients. Anyways, or it doesn't include an ingredient section. It just says, this is how you would make a something or other. Doesn't even say what it is. But that's okay. Maybe pancakes or something. Put it into the pan. Anyways, I think the key thing here is that things are in order, right? So we're going to talk about that in a minute. We have this idea of sequence, that if we have a number of things, one before the other, that's the way that they are performed, right? We don't enjoy before we preheat the oven, right? Preheat the oven is here at the top because we do that before we do all the other things. There's a reason for it being there. Okay, and now in pseudocode, as mentioned, pseudocode has some rules. And to be honest, you know, I think you would say fairly that there's more than one form of pseudocode, you know, depending on what rules you want to apply. But in this pseudocode, when we declare when we're going to use a variable, we're declaring it and giving it its variable type. Type means what kind of type of data is going to be there. This means that this is going to be integer data. And we've got another one here, which is float. That would be important if we're going to do average, because if we do any division, we're quite likely to get a value which would be a decimal value, not an even number. So yeah, so there's a algorithm in pseudocode, same kind of idea. You can see the sequence, declaring variables, then doing a couple of operations, and then doing some output. What would be the output of this? Let's see. We take the numbers 3. They're going to total up to 16, right? Then we're going to divide them by 3. 16 divided by 3 would be 5.333, right? You know, that. Another algorithm, this time using using a flowchart. And I hope by now you're already familiar with the idea that each of these shapes has a meaning. So the shape with the rounded edges, that means it's a connector. Connectors are used at the start and the end, but they're also, the reason why we call them connectors is because we can use them at the bottom of a page and say, go to the next page, you know, go to page 2. And that top of page 2 will say, you know, start page 2. And so you could have a flow chart that was more than one page, and then the connector would be used in that way. All right, so algorithms, what do we have in our algorithms? Well, we must have some instructions in our algorithms, things that happen. So I guess we would say instructions, actions, and processes, things that are being processed, things that are some work is being done. Programming constructs, you'll learn a lot about constructs in programming. Programming constructs like using loops, you know, a while construct, if then else construct. We have constructs for multiple choices, like a case construct. Those things can all be included in your algorithm. Now, interesting point that they've made here at the bottom. and I'll bring up the notes because maybe there's something useful there. But interesting point there is you can have an algorithm and you've gone and worked out this algorithm. It looks nice to you, but it's not correct. You know what I mean? The logic that you've put in your algorithm does not do what you're hoping it would do. And so we actually will check our algorithms. It's not just a matter of just writing them and, or doing the diagrams, whatever. We have to check them to see that they are actually correct. And the other thing is they could be correct, but maybe they will give you the answer, but not in the best way or efficient. I hope you understand the word efficient. Probably you do, but I'll just give you my definition of efficient. Efficient is when you get the most for the least, then it's efficient, right? So if we're buying things, if we're going shopping, we'd want to get the most stuff for the least money. If we're working, we want to get the most work done for the least amount of work. That's efficient, right? And that's what we want to do with our computer programs. We want to get the most work done for the least effort in the computing. Now, what do I mean by effort in the computing? If we have lots of loops happening, we have lots of, we'll talk about this later. It's a bit early in the course to be talking about recursion, but we do talk about recursion later. I mean, there's a lot of words that we use in this course that don't mean much now, but will mean a lot to you later in your studies. Recursion's one of those. Recursion is where a part of a computer program calls itself. All right, it repeats by calling itself. I'm just gonna, you can have a function which calls another function, but you can have a function which calls itself, and you can get into a lot of, what would you call that? A lot of inefficiency there. And so there's a number of different ways of sorting or searching for items in a long list of items. If you've got 100 items or 50 items, probably doesn't matter if you take the most efficient way of sorting them, because computers pretty fast. You could take a very inefficient algorithm and sort 100 things and it'll still just do it in less than a second. But what if you got 1 million records, right? You could really, if you have it could really make a difference how efficient your code is. The other one I would say is we were talking about in the last lesson about relational databases. And I mentioned one of the relational databases that we all seem to end up working with is SQL. And there's different variations of SQL. And the free one, that because it's free, many people will use it, is MySQL. But in any SQL, you can make mistakes in the way that you formulate your queries. We call them queries. So how you build the query, you can turn you can make it so inefficient that it will stop everything else from working. And actually, I have an example of that from a work that I used to work in a telephone company, and a couple of the engineers there got onto this idea of using SQL for a better way of managing the service provision. And whereas before we were using network databases are hard to work with. If you want to change your reports, you have to get a programmer to write a new report. I mean, it wasn't easy. With SQL, and you'll see this because you guys will be doing SQL, with very little training, a person can go and make ad hoc reports, we call them, and get out really, really good information. So this was very appealing to some of the engineers, and they went and bought a bunch of mini computers, installed SQL databases on them, and they're going to have this totally distributed network of SQL servers on which they are going to allow users would be the managers in the different little towns to get queries on their databases, which they were never able to do. Now, the problem was with that system is that it did require updating to a master database, and those master databases were only in Sydney and Melbourne. And they went along with this system. They built this system. They spent like 2 years building this system, right? Millions and millions of dollars on this system. The day they went to launch the system crashed. Now, why does it crash? because they hadn't analyzed. Engineers, right? You'd think that engineers, the first thing they would think about would be the network, but they had analyzed perfectly the computer system, but they hadn't analyzed the network traffic. And doing those kind of ad hoc queries are going to be inefficient, and the network was not able to handle the traffic. And long story short, the project manager of that, that was a nice job that he did for 3 years. But when it went live, that was his last day at work at the telephone company. And that system was never implemented. There was a few other people that was their last day of work as well. Yeah, good times. So yeah, we want it to be efficient. We don't want to have those problems, right? Where we got this system, which is perfect, was giving perfect results, but crashing the network because of inefficient, too much traffic. You'll see that also in, I saw that there, okay, that was a long story. So why do I give you that story? Because it's important. As I said, that was important to that guy. I mean, he was out looking for another job after that, right? It was important to the telephone company. They lost millions of bucks. And then they ended up not being able to satisfy their need. It'll be important to you in your studies here at the college, because you'll be studying, well, how to do searches and things like that. And you'll be introduced to the concept of the big O. Okay, so I'm not going to explain the big O to you. I'm just saying the big O, remember the big O. You'll probably have an assignment on the big O sometime in the next semester or whatever. But the big O is a measure of efficiency of computer systems, right? You'll see that when you do it. And so I guess what I mean by that is it's so important that we actually have a concept on it. And it's so important that we have computer science students put a fair amount of their time into looking how to do things efficiently. So it really is important. Now here it mentions this concept of the industrial PC. I'm not sure why we need to talk about that. We want robustness in our computer systems. So some computer systems are working in dangerous and dirty chemical environments in factories or whatever. And so what they'll do is those computer systems will be hardened in various ways. So you can harden the networks and you can harden the individual components. So for example, instead of just having a normal laptop, you might have a laptop which has some kind of hardened metal, titanium or whatever. Right? Yeah, I've seen some of these advertised, they drive a truck over it and it doesn't break, that kind of thing, right? Of course, they cost like 3 times as much as your normal one, but it can be used in extreme circumstances. People use them in factories, military, like that. Okay, so program constructs. Here we have our favorites. These ones you'll know off by heart pretty soon, I think. They're the basics of computer algorithms, the basics of computer programming, right? We work with these 3. It boils down to these 3. So we have sequencing, which means that if you have a bunch of lines of code in a program or in an algorithm, the one at the top is the first one, right? The next one is the next one. That's how it works, right? They're in order. Iteration means, well, actually, we can change that order. So what we can do is we can repeat a bunch of lines of code. And so we have some ways of doing that. Now, the first computer programs, and we started this course talking about first generation programming languages, second generation programming language, they would do a thing called jump. And so they'd be at line 1, do this, line 2, do this, line 3, do this, line 4, jump back to line 1. You know what I mean? And so that's how they would do an iteration. But of course, you can't just say jump back there. You'd have to have some condition. If something, then jump back to line 1. And so that's how they did it. Now our programs are a little bit easier for us to work with, instead of having to just make them easier for the computer to work with. So we have our high-level languages and our very high-level languages. And so we have these constructs that allow us to do things like do while some condition is true, do a bunch of stuff. It's a lot easier than saying jump back to line 10, right? And the old way of, the second generation programming language, that way, people used to call that spaghetti code because, how do you trying to read through it? Okay, I'm at line 10, jump back to line, all right, and so where am I? So with the constructs that we have in our modern programming languages, it's a lot easier for us to look at and understand. So you have a for loop and you have a while loop. And I think we'll use both of those. I don't know, in this course, we'll use at least a while loop. But the idea being that we can stay doing a bunch of operations as long as a particular condition is true. Or, yeah. Oh, sorry, I missed one, right? And the last one is selection logic. If this condition is true, then we do this stuff. We do that stuff. And the else means that we only do it if that stuff's false. So either this condition is true or false. If it's true, we do the stuff at the top. If it's false, we do the stuff below. And that's kind of a nice sort of thing. And there's variations of that because you can have an if statement without an else. But, I'm not going to go into that now. We can do that later. Sequence, get the idea. We go from top to bottom. And what's nice here is we actually have a nice little diagram to represent that. If you had this as a problem, maybe like you're writing a games program or something like that, the problem that you have is you want to get the blue sphere or ball up to the exit. The operations that you have is move up, move down, move left, move right. So you can see that what you have to do to move, I guess that's right, yeah, and then up, up. So that must be in the right order. If you try and move, you got to move up twice, right? But you can only move up after you've moved to the right. If you try and move up here, you're just going to get stuck there, right? So you have to move to the right, then move up. So the order is important. That's what that's about. You can't move up until after you've moved to the right. Yeah, but you do have to move up, but only after you've moved to the right. And this concept should be familiar to you through your studies in high school mathematics. So you've been introduced to the concept of BODMAS, right? BODMAS, brackets, exponents, division, multiplication, addition, subtraction. Anyway, so order of operations, right? So you know that if something has brackets around it, we do what's happening in there first. Then we look to see if anything's multiplied or divided, then we do them next. And addition and subtraction are done last. So if you had a statement like this, how would you do it? You don't do, the wrong way of doing this would be to say, oh, that's 7 times 2, that's 14 plus 8, that's 22. That would be absolutely wrong, right? What you have to do is, and brackets make it easier. If you're not sure, just throw in some brackets, right? So that's going to be 10. You're going to multiply that by 4. That's going to be 40. And then you're going to add 3. It's going to be 43. So we're actually doing this last because there's a multiply which has to happen before the adding. And so we can see that here they're not doing that, but we also see sequence. If we got these two numbers, we got a 2 and we add 3 to it, that'll make 5. Multiply by 5, that'll give us 25. We got the same 3 numbers, 2 and 3 and 5, but we changed the order and we get a very different number. If we take 10, add 3, it's 13. So I hope that's clear. It's obvious to us when we're doing mathematics, it's very important that we have things in the right order. So yeah, I recommend brackets. I don't think you can have too many brackets in your, you'll know that sometimes you don't need them because you know that your multiplication happens before your addition, but maybe other people can't remember that. I know that people can't because they do it wrong all the time. And the last thing there is about this video, and that video is that video is here. I'm not going to show you that video. You're going to watch it yourself sometime. Please watch it. Okay, please watch the video. It's 4 minutes long, so it's it's just a nice explanation of an algorithm from the Khan Academy. They're kind of famous. So what I want you to do now is I want you to click on this link and register with code.org. So you need to get on to D2L and do that. Now, when you do, I'll know because I have an account with code.org. Am I logged in? Not yet, but I'll sign in. So I'm signing in with Google. That's how I made my account. All right, so I'll show you what I mean. If I look at my dashboard, I can see I've made a thing here for section 21, and actually 2 students have already signed in. This is our login details. We're DNCFDT. So as I said, all you need to do is click on that link and then follow the instructions. But when you do, it'll take us, make sure that in the link that you click, it's DNCFDT. And if you do that, then I'll be able to see you joining my class. So, all right, so one person's done it since I looked. So there's 3 people there now. So you'll see, I can see, oh, look at that. There's somebody who's got a head start on us. Now the green means that they've completed that task. And so what I'm going to do is that's how I'm going to measure, did you do what you're supposed to do? Is I'm going to look at the green and see, did you do it? All right. It's pretty easy, right? So it's not like I'm going to be, looking. Yeah, I have to see a green on your thing, right? Get any more? So that was 3 people. All right. Yeah. So a few more are doing it. So we can see your accounts on there. So you know that that's real. You need to then find that. So when you joined this section, you signed up for the Express course. See, you're in the Express course, and the Express course. Yeah. So it has these lessons in it, and you have some little videos that you need to watch. And it's going to take some time, to be honest, but you have to do lessons for week. You have to do lessons 1, 2, and 3. So lesson 1 is, and there's a bunch. Now look at this. There's 1 video to watch, is to do 9 practices to do. Well, plus 20 practices, I guess. So there's a bit of work to do, right? It looks like there's maybe 13 things there. Yeah. So yeah, you got but it's fairly easy. I mean, each one of these little circles is like 2 or 3 minutes work. I mean, it's not like hours of work. And so you need to sort of work your way through all of those. So for this week, you got a week to do this. For this week, you need to work through lessons 1, 2, and 3. Collecting treasure. Yeah, that's it. It's collecting treasure with Laurel. Those are the 3 things that you need to do: Angry Birds, debugging, and collecting treasure with Laurel. So you guys all sign up. So let's see. It's easy for me to see now, right? Oh, come on. I think I'm going to stop the share now because I think we got enough. All right, Sammy. See you later. So I'm going to end that. I'll put that video up